Okay, I think I'm all hooked up here. If folks can hear me, if they could maybe chime in on the chat as we normally do, that would be great. Let me know if you can hear me okay. And if you can see the screen as well. Oh, a little feedback. Okay, looks like I'm getting some folks jumping on. Some of you were turning and burning here straight from the Nick circus to the sideshow over here. So appreciate you coming on board. Hopefully you had a little chance to get a drink, go to the bathroom. Hopefully this is at least as entertaining as a good Nick live stream. And I will try really hard to minimize the coughing. I'm recovering from the whatever crud I had over the last week or so. So if there's a little bit of coughing, I will try to cover the microphone and not make it annoying. So great. So yeah, let's see some folks here. Ontario, Canada, awesome. Some other people from Wenatchee, lots of Nick fans. Love to see you trying on a different geologist now and then, just to mix it up a little bit. So we'll give it about 5 more minutes and then we'll get going. Yeah, someone asking about Manan Buttes. That is on my list. I will head over to Manan Buttes as soon as weather conditions allow. That might not be till February or March, but it's definitely on my list. It's an area I know really well. If you're not sure where that is, that's in eastern Idaho. It has a really cool excuse me, history with a volcano erupting in the path of the Snake River and diverting the river and essentially tapping into river gravels as it was erupting. And it's a pretty cool spot. Pittsburgh, welcome, Dan. Yeah, and thanks to those who, yeah, Dan had asked me to kick this back an hour. You know, I watched some of Nick's stuff, but it's hard to keep up. And to be honest, like I don't know as much about that area, the Pacific Northwest, as maybe I should. I feel like I'm sort of spread pretty thin trying to keep up on research and literature in my neck of the woods and my area of interest in the area I went to school in, to the south in Utah and down into Arizona. Probably have a little bit more of a stronger pull that direction versus up into Washington and Oregon. So definitely interested in it. And I watch and learn when I can, but shoot, he was doing something like 3 live streams a week this week. So, and I had finals and grading and I was sick and anyway, so I try to keep up, but yeah, but Dan had mentioned that that mine was going to overlap with Nick. So I kicked it back an hour. So hopefully that works for, or worked for a lot of you to not overlap. And by no means did I mean to do that. I just was completely oblivious to when his were going on. So thanks, Dan, for letting me know. And I'm happy to make that that little arrangement there. So Pennsylvania, Fall City, Washington, Drain, Oregon. Awesome. Great. So yeah, so we'll give it a couple more minutes here, and then our focus today is going to be on this earthquake that occurred yesterday, early yesterday morning, about 2:30 a.m. on I guess Tuesday morning, Monday night in Northern California. Just maybe share some perspectives with you, let you know what I can. By no means an expert, but someone who's trained in structural geology and understanding how faults behave. Might be able to share some insights. And then please remind me, in case, so I don't forget, that at the end, I do have a couple things to kind of button up the Hawaii story, because I kind of took off. Actually, it worked out well because the last live stream I did on Hawaii, was pretty much as it was dying down, and there really wasn't necessarily a need to have another one moving forward. So that eruption fizzled out and ended. But there's some interesting data we can look at. I've got some images and then sort of a looking forward, like what will happen next in Hawaii, because I'm definitely interested with taking students there in May. Great. Yeah, Nick's been busy, all busy. Yeah, people in Arizona, Utah. Yeah, I've got big plans for next year. So so look for some more field videos when the weather allows. I got quite a few trips. Again, Big Island, Hawaii, so I'll try to do some videos there. I'll be in Iceland in May again, and so I'll try to do some videos there. In February, I'll be cross-country skiing in Yellowstone, so I might do something there. In March, we are going to be in southern Utah doing some canyoneering. So, again, I always just bring the camera, and any place I feel like I've got a good spot to tell a story in a fairly short amount of time, I'll go for it. So, and then next fall, I have a sabbatical. And so I'll be traveling a lot around the West, hitting especially some national parks and doing some videos there as well. That's basically my sabbatical project, is doing some of that. So anyway, so you look for a lot more. And I will put together, I'm going to come in tomorrow before I sort of hunker down for the holidays. And I think I've got outlined my next videos on sedimentary rocks. Well, the first video on sedimentary rocks, but the next video in the rock identification series for those of you that are enjoying those. So some things to look forward to. Maybe another minute or so and we'll get started. We're kind of few in number, but 41 of you is great. That's a great audience. I'll take it. And then we'll see where this kind of goes here. But I did have some time to prepare. I've got some stuff I hope you find interesting, and we'll see how it goes. But hope you're all doing well. Hope you're all ready for the holidays in a safe, warm place. Cold weather descending upon much of the North American continent. We actually had a warmer day here. It was probably 40-ish degrees. So it actually felt quite a bit warmer today. Sun was out for a little bit. Other folks coming in, Ventura County, Des Moines, Iowa, Calgary. Boy, it's got to be colder up there, I would guess. Stockton, California. Almost had a job there once, a long time ago. Yeah, 3 hours away from the earthquake, Central Valley. I've been through Stockton. And Grayson, Kentucky. Great. So, well, my clock says 5 o'clock, so we'll go ahead and get started here if that sounds good. Hello and welcome. My name is Shawn Willsey, geology professor at the College of Southern Idaho. And I am here with this live stream to hopefully shed some light and answer questions and give you some information related to the magnitude 6.4 earthquake that occurred yesterday in Northern California. As always, I encourage folks to like, subscribe, and share, do all those sorts of things. I'm probably a terrible YouTuber because I don't do enough of the things that grow the YouTube following, but I'm learning as I go. So do all those things if you like what you see here. I think we've got people here that have tasted the Kool-Aid, have watched a lot of my videos and like it. And then there might be a few of you that have, sort of sampled the Kool-Aid and you're not quite sure yet and you're kind of feeling it out. And then there might be some new people that are tasting this kind of geology education content for the first time. And so I hope you enjoy, and I hope you like what we have to put together here. So I'll just go ahead and get started. Here's we'll start with the USGS data, which is always a good place to go. This is an earthquake map for the last day and a half or so since the actual event took place. And I guess to give you some of the data right up front. So this was an earthquake that occurred about 2:30 in the morning Pacific time on Monday night or early Tuesday morning, December 20th. It was a magnitude 6.4 earthquake. It occurred at a depth of about 10 miles or about 15 kilometers and with a location a little bit southwest of Ferndale, south of Eureka, in Humboldt County, and it was just offshore. So if you look kind of closely here, the blue dot is the main earthquake event, the 6.4 event. All the other dots are mainly aftershocks that have occurred since that time. But you can see that that occurred offshore. And again, the earthquake depth was about 11 miles or so, about 18 kilometers down. Unfortunately, this earthquake did have 2 reported deaths, although I did see that it wasn't so much like deaths in terms of structures failing and collapse or something like that, but actually medical conditions related to earthquake and EMS crews getting there. So I'm not sure how they calculate that and make those decisions, but nonetheless, a tragedy. And I can't remember the last time we had any earthquake-related deaths in California. It's probably been a few years, maybe a few decades. I don't know. Someone could probably answer that or look that up, I suppose. But there was a dozen or so injuries as well. Power knocked out. I think there's still power not on in some of the communities there, so they're definitely struggling. And our best wishes and thoughts go to them, and hopefully they can get things fixed and turned back on. There's some structural damage to homes, some buildings, some roads, a bridge, and so that's kind of the latest there. I'm sure you can get onto some other news sites though and see sort of the human impact. But what I want to focus on is sort of the geology behind this, like why this happened, why this happened in this location, and maybe provide some context for what exactly took place here. So, so here's our big regional image here. If you can see this well enough, and I hope you can, there's some thin red lines on here. Those are our plate boundaries, which are also faults. So remember that all plate boundaries are faults, but not all faults are on plate boundaries. So this red line here coming up from the Salton Sea region up through Southern California, just right through the Bay Area here, excuse me, and up to the location of this epicenter. This is the San Andreas Fault. You can also see 2 other red lines take off near the epicenter. There's a red line that heads out to the west into the ocean, kind of zigzags up. This is the Mendocino Fracture Zone or Transform Fault in here. And then we have another red line that continues just offshore up through Northern California into Oregon and Washington. And this is the Cascadia Subduction Zone. And so what we have here, to kind of show this in maybe a little better view, let me switch over to some pictures here. You've been looking at this for quite some time. Pictures, where are my pictures? Let's go here. So sort of just big picture view, what we have going on is we have 3 plates that all converge or meet or intersect right near where this earthquake occurred, at this area called the Mendocino Triple Junction. So you have the North American plate, which most of us live on. I'm here up in Idaho, just right on the edge of the map here. You could be some other part of the North American plate. Some of you are in other countries. Some of you might be in Southern California or the San Francisco region, and you might be on the Pacific plate, which is here in yellow. And then we have a smaller plate here, this blue plate, which is commonly referred to as the Juan de Fuca plate, but it actually is 2 separate plates that are kind of divided. There's actually a fracture zone that extends across this transform boundary here and divides them, but they're moving in the same direction. They act as one cohesive unit. And so let's call it the Juan de Fuca plate, but technically, if you see references to the Gorda plate, that would include this southern part here. And so what we have here is we have the San Andreas Fault providing the lateral or sideways motion between the North American plate, which is moving very slowly to the southwest, juxtaposed against the very rapidly moving to the northwest Pacific plate. And so the Pacific plate, again, moving, let me change colors here. So Pacific plate moving in this direction like that. Our plate, even though you see this little arrow down here, that's just the relative motion. North American plate's actually moving in this direction. But relative to us, the Pacific plate is moving so quickly that the motion across the plate looks something like this. And then we have the Juan de Fuca, the Gorda plates, this ocean plate that's slamming into North America in somewhat of this kind of manner here. And that's what creates this subduction zone. I know most of you, a lot of you watch Nick's Zentner's videos, so you know all about the Cascadia subduction zone and the Cascades. Maybe you live in that region, but just providing a little context for those that might be might be new. And yes, there's another plate up here to the north called the Explorer Plate. I just noticed David's comment there. So yeah, so this plate's a little bit bigger than what's shown on this map and does go up into the offshore British Columbia region as well. So what we have then is in most of California is it's fairly simple, although in the details it gets messy, motion between these two plates, strike slip or transform motion, where most of the motion is sideways horizontally. Very little of the motion is up and down. And so consequently, we have the San Andreas Fault that starts well south of California in the Gulf of California, comes up into California, slices through the western edge of the state, and then effectively terminates right here. And where it terminates here, this is where it intersects the Cascadia subduction zone, which heads up to the north, and the Mendocino transform boundary or fracture zone, which goes off this way. And so we really have these three plates, the Juan de Fuca in blue, the Pacific in yellow, and the North American in pink or red here, intersecting at this location. And this is what we call a triple junction. And there's more triple junctions on the Earth than just this one. There's a good example of another one's over in the Afar, Saudi Arabia, Gulf of Aqaba region. There's some there. There's any place where we get three tectonic plates intersecting, we get a triple junction. So let me show you, let me move forward one here and kind of zoom in a little bit. This a little blurry here, but hopefully this shows sort of the same thing. So here's the Mendocino transform fault. This is the termination or end of the San Andreas Fault right at this location here. The Gorda plate, again, moving to the west or east underneath North America. And so, excuse me, this is the location where this earthquake took place. So if we then go to back to here, look at some of the USGS data, we can see that's pretty close. I mean, there's the actual triple junction there. The earthquake was fairly close to that. And this is a busy area for earthquakes in this region. I'm going to show you this with a couple animations over, I think, a 40-year period to show you how often we get earthquakes in this part of California. When you think earthquakes in California, you probably think of Southern California. You think about the big one. You might think about the Bay Area in Northern California, and that's that's where a lot of the people are. So that's where a lot of the notoriety and attention is drawn. But this part of California is actually an incredibly active and robust area when it comes to earthquakes. And it should make sense because we've got these plates moving in different directions, right? We got the Pacific plate trying to speed off to the northwest, the Gorda plate trying to move to the east, and then the North American plate kind of sluggishly moving along to the northwest. So it's this amalgamation of conflicting motion that creates kind of a complicated scenario here in terms of the geology. Okay, so it's a busy area, and so we've got this transform boundary, another transform boundary, and then the start of this subduction zone here. Let me go to the video, which I think is just really awesome. So this is the Pacific Tsunami Warning Center, put together a great little video clip. I'll let it run and I'll probably narrate a little bit over the top of it. It just barely shows, the bottom of the map just barely shows this area where the Mendocino triple junction is, but it focuses on the Pacific Northwest. But you can actually go to their YouTube channel and there's one for the entire state of California. I believe there was one for other areas of the US as well that shows something similar to what I'm going to show you here. But here's again our basic plate tectonic setting, subduction zone where one plate's diving beneath the other. Here's the place where the plates are spreading apart. Here's a place where the Juan de Fuca and Pacific plate are sliding past each other. So similar to the San Andreas Fault. And then, Yellowstone and St. Helens just for kicks, I suppose. But what I'll do is I'll just let this thing start going. And what you're going to see it's kind of a visually overstimulating video because you'll see flashes of light, which indicate earthquake locations. The bigger the circle, the bigger the magnitude. And these are going to go from 1979 to 2019. So we're looking at a 40-year period. And what I want you to kind of focus on, and it's a lot to digest, but I want you to kind of pay attention in the bottom center part of the map here and see how much earthquake activity this area gets over this period of time. So hopefully we're running. Here we go. So there's the scale. And here we go. We're in 1980 already. And you can see big earthquake there, you know, and you could look these up historically. You could go back and look at the video. But what nicely shows up here, and then the circles get smaller and they sort of fade out. But no matter what period of time we're looking at, over what decade or several year period, we can see the earthquakes kind of forming, at least in this map view, we can see some concentrated areas, right? We've got this area around the Mendocino Triple Junction, some of these areas here between the Juan de Fuca and the Pacific Plate, where the plates are spreading. A lot of earthquake activity in different parts of Washington. What's interesting is Oregon's really quiet. Like, you just don't see a lot of Oregon earthquakes at all. And then back here away from the plate boundaries, we have the Intermountain Seismic Belt, which comes up through northern Utah, comes into southeast Idaho, encapsulates parts of the Yellowstone region, and then kind of swings around kind of like a parabola. It includes some of these earthquakes in central Idaho, and then up into Montana. So actually, I want to go back a little bit just because I'm from Idaho. I want to make sure you see the Boar Peak earthquake in 1983. Should be October. So these are all, you'll see this big one, boom, right there. There's the Boar Peak earthquake, and then it kind of fades it out, aftershocks. But again, focusing on the Mendocino Triple Junction, we can see a lot of these earthquakes here. It's a very active region for earthquakes. So this earthquake we had yesterday in Northern California, not a surprise in terms of the location, in terms of the magnitude. None of these things caught us off guard. This is what we expect, and this is what we've seen in the past in this region. So you can look up some of these individual earthquakes here. It was kind of fun to watch this earlier. Excuse me. And just kind of look at some of these earthquakes, you know, some that I remember or have knowledge of, like, oh yeah, I remember when that one occurred. I think the Nisqually quake in Seattle, I think that was 2001. That one should pop up somewhere in here. There you go, boom, right there, big purple dot over Washington. Yeah, just a great animation, just putting together all this, you know, 40 years of earthquake data, even the small ones. I mean, you know, the fives are fairly small circles, but some of these little dots in here as well. And then at the end here, I'll let it go till it gets close to the end, because I do want to pause it, because at the end, what they do is there's a screenshot of all the earthquakes for the entire 40-year period, which I think is really instructive as well. Again, you can really almost like just pick out some parts of the plate boundary on these divergent plate boundaries out here in the ocean just by the location of these earthquake epicenters. Just fantastic. 2016, yeah, the Intermountain Seismic Belt humming along with some small to moderate earthquakes, but the big ones are out here. The plate boundaries produce the most frequent and the most consistent earthquakes, which is what you'd expect. So somewhere in here, they should throw them all together. And so I'll pause it right there. Very pretty, but a lot to digest. So now what they've done is taken all the earthquakes, allowed the earthquakes to stay at their size based on magnitude. So there's the big Bora Peak earthquake in 83 over here. This is the Wells 2008 earthquake in Nevada. Some of these other ones, I guess I'm just not as familiar with, but these are all pretty big earthquakes here as well. And you can see some of these big circles kind of overlapping in this region. Yeah, Christmas lights, Rachel, it perfect. They're the right colors and everything. But there you go. That might be a fun, if you need another YouTube deep dive. And I'll real quickly just open up their site and show you that they've got some other ones in here. I was in, what was I in? Earthquake animations on playlists. No, that's not what I was in. Although that might be a good way. I think if you just go to videos, there's all sorts of good stuff here. But if you're from California, you might get a kick out of seeing the same video, but just for California. So you can do the same thing and watch California and Nevada. Yeah, more Christmas lights. There's ones for Hawaii. Anyway, I just wanted to give them a little bit of publicity, because just a really impressive site with some really fun videos there. So hopefully that helps a little bit. But the whole point of that exercise was to dazzle you with the Christmas lights, but also to show you just how many earthquakes we typically see in this region. And this is just what we've seen over the last 2 days, I suppose, not even 48 hours since the main earthquake occurred here. We've got 138 earthquakes. So we've got about 130 or so aftershocks that have occurred in this region. And so most of you probably know that, we typically see a main shock, a main earthquake, the main event, if you will. And then afterwards, we see smaller earthquakes that are generated in the same region, maybe on the same fault, maybe on other faults, but in the same region after the main earthquake has occurred, primarily due to, excuse me, the reorganization of stress. This earthquake has just broken rocks, allowed rocks to shift in the subsurface. The fault, rocks on either side of the fault have shifted a little bit. And so now that the new stress conditions have changed, there's adjustments and other fault movements and earthquakes happening. So what we'd expect is more of these earthquakes to continue. We'd expect more aftershocks to continue in this region. We would expect the aftershocks to be smaller than the main 6.4 earthquake, which is good for people living there, but it can also pose its own hazard because you can sometimes get the main earthquake, which is bigger, that destabilizes structures or weakens houses or roads or something like that. And then the aftershocks come, and that might actually cause more damage because you've already weakened that with the main shock. So you'd expect these aftershocks to continue for not just days, but weeks and potentially years following this earthquake. What you can also kind of see here, and I'll come back to this, is there is a crude linear trend to the aftershocks. And so without knowing anything else, this is suggestive, but not concrete, that this may be the actual orientation of the fault plane. So just knowing nothing else, we might look at this data, excuse me, and surmise that we're looking at an earthquake that strikes almost west to east across this region, just because we see somewhat of a linear trend there. And so we'll come back to that and see if that holds up a little bit. Let's go back to some of the USGS information and see what they have to say. So let's actually go into, so if you go into the individual earthquake, you can click on that earthquake. And I'm going to show you some of these other links here. Some of you probably explored the USGS earthquake website for other earthquakes, but I'm hoping I can give you some information and some techniques that might help you in analyzing not just this earthquake, but future earthquakes that occur here or in your region or whatnot. So let's go first to, so we see the raw data here. Let's go to, let's go to, did you feel it? And so what we commonly see from earthquakes is we get a magnitude, right? And so the magnitude is a quantitative measurement of the energy that the earthquake released. So we had rocks breaking in the subsurface, this faulting event. There was the fault, rocks across the fault shifted, rocks broke and moved, and that released energy that reverberated out, excuse me, through the Earth's crust and generated enough energy that we quantitatively put that at a 6.4. And I'm sure you all know earthquakes well enough to know that, well, okay, like a 6 is bigger than a 5. And in a previous video I did on, I guess a couple of years ago, on the Idaho earthquake in 2020, I went over how you can actually compare two earthquakes in terms of how much bigger they are than the other. So I won't go into that now. Maybe if that's a question someone has at the end, I can dive into that. But this is just how big the earthquake was in terms of energy released. But this number, the magnitude, doesn't really tell us much about what it did to people and structures. Now, it can tell us a lot, right? Like a magnitude 6.4 earthquake is big enough that, and it's shallow, right? So it's a fairly shallow depth as well, about 10, 11 miles down, that I'm thinking, okay, this earthquake possibly caused damage that adversely affected humans. But how do we really know that? And so what we actually do is we rely on sort of citizen science and data that comes in from people to generate what's called a shake map. And so if we look at this shake map here, we'll zoom out a little bit. What you're seeing with all these little squares are people who hopefully, whoops, let me go back one. Hopefully after, they made sure their their house was okay and their pets and their loved ones and their neighbors, have gone onto the USGS website, answered a short questionnaire or survey about the earthquake and how it felt to them. And then all that information gets compiled by the USGS to determine these shake maps. And what these shake maps are useful for is it shows us where the strongest shaking was at the ground level. And now typically it's not, it's not rocket science, right? Like you can see the star there, that's the epicenter. And where do you see the deepest colors? And these go from like blue to green to yellow to orange to red. Sure enough, you see that the deeper colors kind of closest to that star there. But that's not always the case. And it depends on a couple things. It depends on the soils. It depends on the rocks. It can depend on the houses the people are living in, the construction styles. If we have a large population of people living in brick, cinder block, stone buildings, we might see an uptick in those regions. So let's say, for example, somewhere over here, maybe, 20, 15, 10 miles away from the epicenter, there's a bunch of older homes, a downtown district with a lot of older buildings sitting on top of muddy, high water table type soils. We actually might see a higher spike here than a place that's closer to the epicenter that has modern wood frame buildings built to code that are maybe sitting on top of thin soils with bedrock underneath them. So you can see there's a lot of factors that go into this. But when I hover over any one of these, or I guess click on it, it's a little hard to see because it's small there, but you can see the number of responses. So 17 people live in this little box, and their combined responses to that survey give us a intensity level, whoops, I keep doing that, sorry, of, in this case, 7. And let's go back to this here, because you can see there's a scale intensity level that goes from Roman numeral 1, technically it goes up to Roman numeral 12, but they kind of peg it here at 10 plus. And this is just a level of shaking that occurred. So this is based on damage. So this is based on people's accounts, damage to buildings, roads, infrastructure, and all that gets put together, and we come up with a determination of the intensity level of the earthquake. And this is probably still being, this is somewhat dynamic, I suppose, but so far we've gotten 5,713 responses. And it looks like the maximum shaking level was about an 8. So you can see that that's sort of a moderate to heavy damage, and sort of shaking is considered severe. And these are all subjective terms. So realize intensity is a subjective measure. It's qualitative based on people's accounts. It's not quantitative like magnitude. We know the magnitude of an earthquake generally within a minute or two of the earthquake occurring, because it's all assessed and interpreted and calculated by computers and measurements and science and math, right? Intensity level is different, and it depends a lot on some of the factors I talked about: buildings, population density, soil types, that sort of thing. So the point is that this was quite a noteworthy earthquake, and an earthquake that I'm doing a live stream on because it impacted a well-known populated region in Northern California. If this magnitude 6.4 earthquake had been on some island off the coast of Alaska in the Aleutians, we're not doing a live stream because no one felt it. The instruments felt it. We know it happened. It's on the USGS website, but we're not seeing thousands of people without power, a couple fatalities, damage, infrastructure, that sort of thing. So realize that these big earthquakes that we hear about are always going to tend to be skewed based on our sort of media bias, I suppose, towards the ones in the more populated areas. I sometimes give my students a question about ranking, which state is number one in terms of earthquake frequency, like which state has the most earthquakes year in and year out. And the choices are, a couple of them, but ultimately it comes down to Alaska and California. And a lot of them choose California, but in accuracy, Alaska has way more earthquakes than California does by far. Okay, so here's, so I wanted to go to the shake map, but all these dots basically are, that's only one response there. We can click on some of these other ones. Yeah. But you get out into some of these other areas. I know there's more people to the north. Here's 616. So there's a heavily populated area in that little zone there. Keep clicking on that, sorry. But anyway, that's how these shake maps get generated, and you can look at those for other earthquakes as well. Some other things I want to show you here. Let's see what I got here. Let's go to the beach balls. And I glanced at the chat there and someone wanted to see these. So for every earthquake that occurs on the USGS website, I believe this is true. Sometimes the smaller ones, you don't see this as much, but definitely bigger quakes like this, excuse me, we get this thing called moment tensor. And actually you can also go into this by, if you go over here to technical on the left here, you can see these little things pop up as well. And so let me explain these things. So you guys are now part of the club. You are now being invited by me to join the technical tab or access the technical tab of the USGS website. And I'm going to explain to you how to read these things. So if we go to this one for the earthquake off the coast of Northern California, we get these little things that we sometimes call beach balls. Officially, these are called focal mechanism solutions or focal mechanism fault plane solutions or something like that. And what these are a plot, a three-dimensional, what they call a lower hemisphere. I'll explain this in a second, but basically it's a plot of where the rocks were squished or compressed and where the rocks were stretched or extended. And by plotting this information up, this tells us a little bit about what kind of orientation the fault has in the subsurface. So what we can see here is you can see there's kind of two lines that intersect in this circle here. And I'll maybe annotate these a little bit as well. So we can see one line kind of coming through here, another one kind of coming through here, dividing this beach ball into into 4 zones. And what this suggests, so this circle is set up with respect to north. So north is up. You'd have obviously west over here, east over here, and south here. So think of this now as a compass rose, if that helps. And so what the seismic data has told us, and then I'll explain more on how these actually form, is that this earthquake, 6.4 off the coast of Northern California, was produced by one of 2 faults, either a fault that is trending or strikes kind of northwest southeast-ish, or a fault that is oriented slightly southwest to northeast like this. Okay, maybe I'll switch to the pen that doesn't vanish as much. I'm on the vanishing pen. Hopefully this is right. That's the wrong thing. Sorry, team. Let's just go back to this one. That's fine. So either we have a fault that goes this way on the map or a fault that goes this way on the map. These are the actual azimuth directions of the fault. So a fault that goes 246, and this one would be 155 if you know how azimuths work on compasses. If you don't worry about it. And then the pattern we have here, where it kind of looks like there's a white zone here, a white zone here, and a blue zone here, and a blue zone here. This tells us that this was a strike slip fault. So we either have a kind of north to south trending strike slip fault that moved things this way. So that would be a right lateral strike slip fault. Or let me go back to, if it'll let me draw. Here we go. So we got a fault going this way. Oh shoot, it's still the vanishing pen. Oh well, you can see it. I'll just keep drawing if I have to. So we either have a fault that looks like this on the map, okay, or we have a fault that cuts across the land this way, but the movement would be in this direction. Let me go to my diagrams now and explain how these form, and then let's decide as a team which fault we think is the true fault, because this isn't going to tell us. This is just telling us, hey, I've taken all the seismic data, put it all together, and you either have a fault that trends this direction or a fault that trends this direction. So let me get out of here and get you to something that will be more useful. Okay, there's my family. That's not what I wanted to do. There we go. Okay, so if we go to this, here's what I want to cover. So whenever there's an earthquake, we record that earthquake as a seismogram, right? And up and down, the little needle goes up and down because the ground is shaking. There's different types of waves that come in, yada, yada, yada. The important thing is that the very first wave that arrives at a seismic station is what we call a P wave or a primary wave. And so notice that this P wave initially deflects upwards. The first motion of the earthquake detected at this location goes up, and then it goes up and down and up and down and up and down. And then there would be more waves coming in if we had more of this. Now let's look at this other earthquake at a different, well, same earthquake, let's say, but a different location. Notice that here, the first motion is down, and then it goes up and down and up and down and up and down. So the important thing here is by looking at these two types of motions, whether it goes up or whether it goes down, that tells us something about the way that the stress is behaving in the earth. So if it goes up, it's a push motion. So the rocks are being compressed. The rocks are being squished together at location A. Over here at location B, with the same earthquake, we have rocks that are being pulled. So the rocks are being pulled or extended rather than compressed. Now, in any one location, this doesn't make much sense. But if you plot this up at a bunch of locations on a map, because remember, we'd have seismometers, sensors, detecting this one given earthquake at a variety of locations. So maybe over here it's up, maybe over here it's down. And so let's call this compression, because that's what's happening here. So we'll give that a C for compression. And this is extension or tension, so we'll give that a T. So let's say on a map over here, I don't know if this will show up, hopefully it will. So you have a C here and a C here and a C here. But then over in this area, you have a T, maybe you have a T here, another T there. And then let's say, I gotta think this through before I just do it. And then there's a T's that are up here. And then over here, there's some C's, okay? Well, this kind of looks random right now. You're like, well, I don't know what's going on. It's just a bunch of C's and T's, a bunch of letters on the map, different locations with different earthquake styles, I suppose. But what we have here is we can actually divide these regions up into something maybe that looks like this. Whoops, let me actually erase just that one. Oh, it took them all away. Shoot. Well, you saw what I had there. So let's say we have something that looks like this. We've got the T's up here. I'm new to some of the drawing tools team, so appreciate your patience. So there's a T, there's a T. And then over here, we had a bunch of C's. There's a C at that location. So each letter is a location on a map. I'm drawing a map right now, some of which these locations recorded tension, right? This type of thing. Here's our T. Oh, now I gotta switch colors. T right here for this type of motion, first motion of the P waves, and some of which recorded C here for this type of motion. And so what we have now are these zones now. So we've got one zone here. We can divide these zones up this way, but we also need to divide the zones up, oh shoot, this way. Sorry, I'm not good with the mouse. There you go. So now I have a region of T's. So we kind of make quadrants, right? A little area of tension. So these areas all experience the same type of P wave motion. These areas experience the same type of P wave motion as well. And then you can see the same thing with the compression and the tension. Well, now what we could say is, okay, I'm gonna kind of redraw the same thing over here, hopefully a little cleaner. Maybe pick a different color. Ooh, green. Green is nice. I do like green. And let's make it fatter so it's a little more noticeable. So I've got one fault going this way, got one fault kind of going that way, right? Well, rocks are being stretched here, but they're being compressed here. So the motion as the P wave has moved through this area is in this direction, okay? So I might have a fault that goes this way that moved things, and on this side I can see that it's in the opposite direction. So I might have, in this case, a fault that strikes from, or that is oriented, oh boy, northwest to southeast, okay? And as I look across the fault, if I'm right here, here's my little stick figure. If I'm standing here and I'm looking across the fault, notice that the motion is to the left, right? So the motion is to the left, so that would be a left lateral strike slip fault. These are getting messy. I'm going to draw them one more time. And I appreciate you hanging with me here with these terrible drawings. So again, our two big faults that divide the tension and the compression things. And then we had either this type of fault, right? If this is the fault plane, if this one right here, number one, is the fault plane, then that's our motion. But if this is the fault plane, number two, here, this fault, then the motion was in this direction, right? Towards the compression. All the C's were up here, all the C's were here. So in this case, we would have a fault that strikes more or less east-west-ish, but the movement is to the right. So we have to figure out what kind of fault we have here. Hopefully that makes sense. So this is kind of the way these first motion, let me get rid of all the drawings, sorry. And done. Okay. So this is the way they work. I don't want to go to that yet. And then what we can see here, oh boy, I'm like not my slickest production here. Where's all my little windows here? Oh, there they are. Okay, sorry team. What that turns out to be, sorry about that, is we end up with beach balls that can look in a lot of different ways. So if the fault is moving side to side, like the one I've been showing you, we get the dark zones, that's the compression zones, and then the light zones, the tension zones, right? So you either have a fault going this way or a fault going this way, and that's a strike slip fault. So if you see a beach ball that looks like this, kind of like a radioactive symbol or something like that, then you end up with these strike slip faults. If you end up with beach balls, or again, fault plane solutions, focal mechanism solutions, that kind of look like this with a white region in the interior, these are caused by normal faults. If you end up with something that's the opposite in terms of the color or the tension compression region, you end up with something like this, where you get this is a reverse fault. So the compression's in the center, and this is a reverse fault. This is what it looks like as a half sphere, a hemisphere. This is kind of what you're looking at here. See how there's two red areas on either side? This is the sideways view. This is the top-down view. If this doesn't make sense, that's okay, team. But what I want you to be able to see is fundamentally, you can look at these beach balls. By looking at their pattern, you can tell what kind of fault produced the earthquake. So these are our three end members of faults, right? Strike slip faults, normal faults, reverse, or sometimes they're called thrust faults. What happens if it's an earthquake or a fault that's sort of a hybrid of these two? Well, that's these last two here. So what if it's kind of strike slip motion, but it's also a little bit of a normal fault? That's what we call a oblique normal fault or a transtensional fault. And same thing here if it's a little bit compressional, transpressional fault. So I probably butchered that. I apologize. Let me get you back on track now. So what we were trying to do as a team is figure out what kind of fault and which fault produced this one here, the Ferndale one. We know it was a strike slip fault. The fault that produced the earthquake yesterday was undoubtedly a strike slip fault, either a left lateral fault that's oriented more or less west to east, or a right lateral fault that's oriented more or less north to south. So sometimes you can't tell, but what you can do sometimes is go back to the earthquake data. And remember, we drew a line here. This is pretty suggestive. And if you look at the orientation of that line, that's really close to that, right? They're probably within a few degrees of each other. So without knowing too much here, and I'm not an advanced seismologist, it seems highly suggestive that this earthquake was on a east-west striking or trending fault. And then based on the fault plane solution, the beach ball, that would make it a left lateral type fault. It is possible that it was something like this, but if we come back to here, we just don't see much of a trend in that direction. So a lot of time what you can do is just look at existing faults. Now, it might actually have been one of those faults. Actually, as I think about it, if we go to the faults that have been mapped in the area, I think we have to zoom out. It's a little hard to see. I don't know if you guys excuse me, can see this, but there are, gosh, it's hard to tell because there's faults kind of going both ways that kind of go northwest, southeast. But there's some that do turn, like this one to the north, that goes more or less east-westish here. And these are even labeled too. Here's the Russ Fault Zone, excuse me, the Table Bluff Fault Zone. So you can actually look at the fault names as well there. But let's see what the USGS had to say, because they had the people that looked at this in detail. And let's see, did I already lose it? Oh, I got to go back to it. Okay, let's find it real quick here. Let's find that big one. There it is, 6.4. And if we come down here, we can just kind of look at the summary here. So let's see what they had to say. So 6.4, in the vicinity of the Mendocino Triple Junction. Okay, we looked at that, the Pacific North American and the Juan de Fuca/Gorda plates. Focal mechanism solutions, we just looked at that. Those are the beach balls. Indicates that the rupture occurred as a result of strike slip faulting on a steeply dipping, that means it's near vertical. The fault plane is vertical. Steeply dipping faults striking either southeast or southwest. And that's kind of what we saw there, that it's one of those two. So it looks like they, at least in this preliminary summary, haven't really decided. The location, depth, and faulting mechanism indicates that this event very likely occurred within the subducting Gorda plate. So what that means is that this earthquake was not on the San Andreas Fault, which kind of makes sense because the San Andreas Fault kind of dies out right here. It was not on the Cascadia subduction zone, which starts further offshore and runs to the north. It looks like, in their opinion, it was the plate that's being pushed beneath the North American plate. That was the plate that broke and generated this earthquake here. Anything else? Let's see, that's important here. Oblique motion. Oh, and then this is kind of fun too. So they actually mention, and you might have picked this up in your news stories, but I went to this as well. So ironically, I know some of the conspiracy theorists out there are going to think that there's some sort of cyclicity to this, but ironically, as happenstance would have it, there was an earthquake in essentially the same region, although it was onshore. Notice this blue dot here is on land and not offshore, that happened 1 year ago to the day. So basically on December 20th, 2021, we also had an earthquake very close to the one that happened today. And let's see if the plate boundaries, there's the plate boundaries there. And so the big one here, if I can find it, where's the big one? It's way in there. There it is. Okay, so it should stay blue now. Here we go. This was basically a year ago. So again, funny timing, right? The same date, but exactly a year ago. Was a 6.2 quake. You can see the intensity level there. So intensity level 8, a little deeper. Okay, possibly on a different system. Though, look at the earthquake pattern here from this earthquake. And let me make sure. Okay, I want to get rid of these. So these are actually different times. I should probably get rid of some of these quakes, because these are actually, if you look at the dates here, these are happening like 10 months before that quake. So this is not a good pattern here. Let's do this. Let's go 12/18, just before the earthquake. And let's go, yeah, this actually might be a good search here. Let's see what we get for, oh, we got too many earthquakes. We need to tell it exactly what area I want to focus on. So we will focus on this area right here. Sorry, doing this in front of you. I meant to have some of this ready. I thought I did. Okay, so now we are looking at only the earthquakes that have happened, that big one from a year or so ago, and the ones that have happened since, but not including the one that happened yesterday. And if we got in here close enough, we can pick out that big one there. We can turn on the satellite view if that helps you a little bit. This also has some of the other earthquakes over the last year or two, but you can see with this one, you know, again, a different trend, right? We're not seeing, the other one we had, the 2022 quake that happened yesterday, was more offshore and had a little different trend. This one actually looks like there's more of, we'd have to see the timing of all these as well. Yeah, these are all aftershocks. It looks like as I click on these, they're happening the day of or the day after, most of them anyway. Some of these might not be, but you could look at it anyway. And then there's another trend over here that's unrelated. So anyway, I just thought it was interesting that kind of fell apart, that there was an earthquake there in the same region, essentially. And here's the beach ball for that earthquake. So a little bit different orientation than what we saw with yesterday's earthquake. And then this is what their summary on this one that happened a year ago. So 2021 quake, not the 2022, 6.2, again, Mendocino triple junction. Interestingly, this earthquake, 6.2, was preceded by a 5.7 about 30 kilometers to the west, which occurred on either a east-west striking right lateral fault or north-south left lateral. Again, why are they not sure? That's the beach ball thing, right? Location and faulting mechanism indicate that the 5.7 likely occurred on or near the east-west trending Mendocino transform fault. So basically what they're saying here is it looks very much like this trend here is very similar to what we see with the Mendocino transform fault. It kind of is the east-west fault that kind of comes offshore here. So anything else I think was there? Yeah, they thought this one also magnitude 6.2 was in the Gorda plate. So same as what we see with the earthquake yesterday. And then they just talk about how common, earthquakes are at the Mendocino triple junction, which is what we've kind of already looked at a little bit as well. So I thought that was interesting. Hopefully you did as well. But that's some of my analysis on that quake. I do want to cover a couple other things that I thought were pretty interesting or important before I get to the Mauna Loa stuff. And that is how successful the Shake Alert program was. So if you're not familiar with this has been recently deployed. I think California's had it for maybe 3 or 4 years, but I'm sure you're all aware of different alerts that pop up on your phone, right? There's a Amber Alert, a severe thunderstorm warning, could be a wildfire thing. There's different alerts we get automatically on our phones at any time of the day, depending on what's going on. And what we've started to develop in some of these earthquake-prone regions, starting I think in Japan and then in California, and this is spread, I believe, also to Oregon and Washington, is a quick emergency broadcast that's sent automatically to your phone if you're within the region being affected by the earthquake. And what it basically is, it's the buzzy sound that comes on your phone, just like an Amber Alert. And then this is what the text reads on your phone. So emergency alert, earthquake detected, drop cover, hold on. And the timing between when you get this alert and when the shaking begins that you would feel might be like the shaking might have already started by the time you get this, which tells you that you're really close to the earthquake's location or epicenter. Or you might get this alert and have anywhere from a few seconds to maybe a few tens of seconds before you feel the shaking. But it's really a cool system. Now, this is by no means a prediction system. What this is we talked about the different waves that come in from an earthquake, right? And so real quick, just kind of as a review, when we get an earthquake, we get, the P waves, the S waves, and then the surface waves, okay? These initial waves here, the P waves, are the most benign. They oftentimes aren't even felt by humans, but the instruments pick them up. Our seismometers pick them up. The S waves, and then these waves here, which are called the surface waves, are much more destructive. These are the waves that are causing a lot of problems. And so the idea is the technology that we've been able to develop here, which is really awesome, is as soon as these waves arrive and are detected, it sends the emergency alert out, basically saying, hey, an earthquake has started, and we don't know how big it is, but we know generally where it is, and the earthquake has begun, and your location, your cell phone's location, is within a region that we think you should take cover, right? So you should drop down, get underneath a table or a desk. If you're in your car, you might pull over, so like poles don't fall down, something like that. At least gives you some warning. And with the earthquake yesterday, it gave about 10 seconds warning to Northern California residents. which you might say to yourself, well, okay, 10 seconds, like, and so the idea is the alert goes out when the P wave comes in. And in this case, in Northern California, there was about 10 seconds time before these more destructive S and surface waves came in. And 10 seconds, and granted, this earthquake occurred at 2:30 in the morning, so a lot of people are probably asleep, but still, that's great. That might give people time to roll out of bed and get under a nearby desk or table, maybe get underneath the bed, get into a position where maybe go grab their kid if their kids nearby or something like that. But basically, you don't want to like start running down the hall and running out of the house at that point. So it was a success story is my main point here. Is there was a couple articles I read about the shake alert system, which had been deployed in California a few years ago, I believe, and had just been implemented recently in Oregon and Washington. But for those Northern California residents and visitors, they got the alert. It worked well. A lot of people said that, yeah, it woke them up and scared them, but at least gave them a few seconds to know it was happening. I'm assuming most of us would prefer that we get woken up by an alert that tells us an earthquake's about to begin versus woken up by the strong shaking and things falling down that might occur in an earthquake. And so just great success story, science, engineering, technology, all working towards the public good. I just thought that was great. And so just wanted to to share that. So awesome. Let's see. I think what I'll do here is I think that's all I had on the earthquake. I have a little bit of a tangent that I want to go on, and then let's do some kind of button up Hawaii. I think that'll only take a few minutes, and then I can see what questions you folks have. And I appreciate you hanging out with me this close to the holidays on the winter solstice on a Wednesday evening. Let's see. Oh, we did that. Shoot. Okay, so I'm not sure how to like say this, so I think I'll just say it. So when it comes to earthquakes, there's a lot of misinformation out there. And so I think the way I want to say this is, I guess, I think I'm preaching to the choir, I'm sure. But you guys are my ambassadors. You're the ambassadors of just good information and good science, and hopefully directing people to the right places. But it's alarming to me. And as a scientist, I've kind of like turned my head and looked the other way at this stuff. But now, especially getting into this YouTube thing, I'm realizing more and more that it's maybe a better idea to kind of at least call out the misinformation when I see it. So to be fair, I have taken this YouTube, or this is a Facebook post actually, from a Facebook site. So I've scribbled out the actual site's name. And I just want to just kind of show you so this is their post on this earthquake in Northern California yesterday. They're basically saying this, insert the Facebook group or site's name here where it's blacked out, has issued an earthquake watch effective now for the next 14 days. So what they've effectively done here is they are telling people that they should be on the lookout for earthquake for the next 2 weeks. Now, that's not too surprising because we just had a big earthquake. Aftershocks are likely. So on the surface, I don't have a problem with that. Let's continue. A magnitude 6.6 plus earthquake hit Northern California early this morning in the red area. So you can see their graphic here in the red. Okay, no problem there. Consequently, it was not along the San Andreas Fault. That's true. Thank you. But it was on the Juan de Fuca's south end. That means one thing. Well, what do you think they're doing here? What do people think about when they think about the Cascadia subduction zone? So right away, at least to me, maybe I'm reading this wrong, so you can tell me if I'm totally out in left field, but they're teasing the alarm a little bit, right? It's clickbait. They're trying to get people riled up about something, and we like to be. I mean, we're a sensationalist culture, right? We like to be, like Yellowstone and super volcanoes, and there's so many things that we see and we click on, and I'm guilty of it too. Some of my titles of some of my latest YouTube videos, because I'd like more people to see them, because I like to share, I know if I put certain titles on things, I probably am attracting more people that way. So we're all susceptible to it on one level or another. But it was on the Juan de Fuca Southern, and that means only one thing. Pink color is the volcano as Mount Shasta. Careful, she is a Mount St. Helens waiting. I'm not sure what this means. Someone have to explain emojis to me. Green line San Andreas Fault pushes here, and we have more stress than ever. So pick one, which I see both happening. So I'm going to issue this again. Get your earthquake stuff ready. It only took a tsunami long ago to change the lives. So to me, I'm sorry, friends. This is just BS. This is garbage. This is totally manipulating people's fears and anxieties about earthquakes and other processes that are stressful. I get that. Just to get clicks and lights and stuff. And to be honest, if you go to this Facebook site, they have thousands and thousands of followers. I mean, you can see 251 shares, 107 comments, and all the likes there. And that was just 2 hours after it was posted. So this stuff's out there. Yeah. I'll see what you guys have to say about that later. I'll let that go for now, but just be careful out there. There's some YouTube channels. There's one YouTube channel. I'm not going to name names. This person has over 500,000 followers. It's like 560,000 subscribers. Watch this person make quote unquote predictions on earthquakes. And it's alarmist, and it's not scientific, and it's somewhat like Farmer's Almanac weather forecasting, I suppose. I mean, I can make a prediction right now, and let's be careful about predictions versus forecasts, right? Predictions are when we specify a place and a time and an event and a magnitude of something happening. So it's like me saying, at 6:41 p.m. on December 23rd, there will be a magnitude 6.2 earthquake in Reno, Nevada, or something like that. A forecast is just, hey, in the next 30 years, there's a 20% chance that this could occur. Anyway, I'm on a tangent. I apologize, a little bit of a soapbox, but I'm just hoping you guys can also fight the good fight like I am, and not be confrontational per se, but just the people you know and trust and love, maybe give them a little bit of direction if you see they're headed off into some of these pseudoscience realms of just, and earthquakes is probably the most prolific one I see out there. Okay, let's switch over to the the Mauna Loa eruption. So I last chimed in with you guys on Thursday, December 8th. And that was about the peak of the thing, or well, I was actually winding down at that point, but I just want to look at a couple USGS images and answer any questions you have, but just quickly let you know that this eruption is completely ended. The flow is inactive. We can actually see here the lava flow, which basically ended on the 11th. So that weekend, I guess Sunday, a couple days after I did my live stream. It ended. There's fissure 3. That was the eruptive fissure that took most of the stage there. And then this flow extends about, if we look down here, it's about 12 miles long. So it's a 12-mile long flow, and you can see the total area covered by the lava flow. So the flow petered out, ended, the magma supply into this fissure waned, and the amount of eruptible magma was pretty much tapped out at that point. Some of the fun images, we don't have to go through all of these, but here's a nice one here that shows, and we'll see what date this is. Close some of these. Computer's lagging. Here we go. So you can see fissure 3, and you can see some of the lava starting to crust over. Not much lava coming up through the vent here. There's the helicopter probably there. Let's see, a aerial view of fissure 3 cone. Yeah, no fountains. So this thing was jetting, right? This thing was fountaining lava for some period of time, but then it started to wane later on. You guys can get on and look at these as well as I can, but just kind of showing you some of the images as the eruption died down. A lot of gases still coming out, flows in the background still degassing a little bit, but the flows have basically ended at Mauna Loa. Similar to that, we haven't seen any And the other thing that was interesting was, and I'll talk about this here in a bit, is that Kilauea kind of died out at the same time. If we go to earthquakes, this is the last week. So here we are, Big Island of Hawaii. If we go back up to Mauna Loa, one earthquake within the last week up here. So a sure sign that the volcanic activity and the movement of magma beneath Mauna Loa, at least for now, has ended. The Pahala earthquakes, that's a different beast. We kind of talked about that at one point. But Kilauea still having a few earthquakes in this area. But not much happening there either. Kilauea actually died. So both volcanoes right now are not active. The little summit lava lake at Kilauea, and we can maybe go in here and find a picture. Oh, I think I've got a summit webcam over here. Yeah, there's nothing happening in terms of seeing active lava up on at Kilauea. On the thermal image, you might see a little bit there because that lava is still cooling, but in terms of active incandescent lava at the surface, that's pretty much died out there. The monitoring data is interesting. Let's see, which one do we want to look at here? So the tilt here, this is an interesting one here at Mauna Loa. You can see the blue line. So there's a little kick here when the eruption got going. And then, so there's the inflation of magma, the eruption getting going. And then as the blue line drops off here, that's the lava erupting. So deflating, continuing into December. A little earthquake right here. That's why there's a little bump. And then you can see about when I signed off with you guys on the 9th or so, the trend of deflation, basically the tilt on Mauna Loa's slopes, had pretty much ended, and then it started to rise a little bit. So this is indicating that it was inflating a little bit. Again, the scale here is very minute. These are incredibly sensitive instruments. So it starts to kick up a little bit here, but then you can see it just flatline. So for the last week or so, flatlining. So had this trend continued, that would indicate that magma is being injected into the summit, shallow summit reservoir beneath Mauna Loa, but that's not what we're seeing. So we'll see if this trend continues. But for now, it does not look like anything will be happening at Mauna Loa anytime soon. If we go back to some of the imagery, or some of the monitoring data, yeah, same sort of thing. And then this is a similar thing here with the vertical motion here with the GPS. You can see it kick up, right? So there's, boom, kicks up because the magma is inflated. So the summit elevation rises, and then it erupts that lava. So it drops, and then it just kind of stabilizes again. So it's actually dropped back down. Interesting. And then the last thing I want to do here, I know this is not nearly as in-depth as some of my other Hawaii stuff, but I don't want to take this too long. Appreciate you guys for joining me. The last cool thing I have for you, and I apologize for some of the technical stuff, still figuring my way around this, is I thought I pulled this up and thought this was really interesting. And again, I'm not making any sort of predictions with this, but an interesting trend. So the big question, of course, is like Mauna Loa and Kilauea's activity and how they because they have separate shallow magma reservoirs, but deeper they are connected to some degree a similar plumbing system. So magma is rising from the same conduit, the hotspot, then it's moving up into their shallow magma reservoirs where it starts to crystallize, and that's where we get a little bit of the different chemistries. But this is a graph here on the top of from 1780 eruptive activity at Mauna Loa. And so you can see we don't have any information until mid 1800s when we start monitoring the thing. But you can see all these lines here are eruptions, some of which are short, some of which are longer. But you can see a clustering in here, right? In the mid to late 1800s, maybe I'll annotate this a little bit. So we've got kind of like this little zone in here of Mauna Loa erupting quite often, and then it's kind of sporadic here, right? But we got a little bit here, and then it just goes silent. So from like 1950 or so, all the way up until today, we only have really 3 eruptions. The one in the late 70s right here, the 84 eruption here, and then I guess we could add the 2022 eruption, which would probably show up. I guess it lasted not quite a month, but so it would show up as a line on here, something like that, right? So only 3 eruptive events in this, what, 70, 60, 70-year period. And then look down here at Kilauea. So when Mauna Loa is active, what's Kilauea doing? Not much, right? So if we look at that same period of time, and I tried to line these up so they were essentially the same. So this is Kilauea here, Mauna Loa on top, okay? Mauna Loa active, Kilauea is kind of quiet, okay? And then if we look over here, I'm not sure what to do in the middle section here, although there's a Kilauea really gets going in around 1920, right? And then there's a little eruptive period here, a little bit of a weird period here. But then this pattern here, I think, is interesting. So then when Mauna Loa is quiet, starting from about 1950 up until today, if we just count those 3 isolated events as just anomalies in the eruptive period, so from about 1950 here up until today at Kilauea, you can see Kilauea going crazy, right? So Kilauea is way more active in this period of time. So interesting. I just thought that was an interesting comparison between the two, that when Mauna Loa is active, erupting frequently over some multi-decade time period, Kilauea largely is quiet with few eruptions. And the converse is true. When Mauna Loa is quiet, as it has been mostly since 1950 or so, Kilauea has been active. And so we'll see what happens. Right now, we think that the shutdown at Kilauea might be more related to Mauna Loa's changing volumes and kind of pinching and impinging a little bit on Kilauea's plumbing system, because we still have the earthquake activity underneath Kilauea. So I guess if I had to give you any sort of takeaway on that, if I had to take a stab at this, I would say that Kilauea is much more likely to erupt next versus Mauna Loa, just based on, again, past activity, the cycles that we kind of see there, and then the earthquake data there. So hope that was helpful. So that's all I got, team. I hope that was a good use of part of your Wednesday evening or afternoon or whatever time and day it is there. I appreciate you for jumping on with me. Not as polished as Nick. I'm working on it. Maybe we'll never get there, but hopefully providing good information to you, hopefully helping you see things through my eyes, with my perspective, and that's of some value to you, hopefully teaching and educating you and explaining things in a way that's understandable. I don't have all the answers, but hopefully that was helpful. So I wish you all a great Christmas and holiday break. Look for a, excuse me, a new rock identification video from me, hopefully by Friday. I'm hoping to do that tomorrow on Thursday. And then probably a little bit of a lull until I kind of get things going again in the new year. We'll see if we can get outside and get some more field videos going. Oh, before I sign off, let me answer some questions. Sorry, I was ready to just head home. Let me scroll back through real quick here and see if anything pops up that I can address. And I know David is on here, and I appreciate David for answering all the questions. So if I see a question and then a David response, I'm not going to read it right now, but I'll assume David, who's very good at answering the questions, is providing good information. Let's see. Yeah, I'm not seeing a beach ball. Hopefully the beach ball thing helped a little bit. Yeah, it gets more complicated than that, but they're actually pretty easy to read once you just kind of see a beach ball and you're like, oh, it's kind of a big X shape. That's a strike slip fault, or it's a big cat's eye. That's a normal fault, or whatever. So let's see. Yeah, David, looks like you were very prolific on here. So iPhone accelerometers to develop earthquake information. I don't know, William Lloyd. That's a good question. Someone using iPhone accelerometers to develop. There's a lot of other information that comes other than from seismometers. I don't know. It's a good question. I'll have to look into that. Maybe David answered it or someone else did. Yeah, lots of Nick fans. Thank you. I appreciate you. Nick's a great guy and kind of, I don't think I knew he was doing his thing, but I kind of started doing my own thing when he was doing other things like a couple years ago. So, but we have crossed paths, and I did ask him at one point to, hey, like, will you let people know that I exist too? Just because it was hard initially to kind of get people on the bandwagon. I suppose. Yeah, left lateral, dextral, sinistral. You guys are using some of the cool words. Left lateral, right lateral. Are the beach ball figures accessible to us? Asked Rachel. Heck yeah, they are. They're right there on the USGS website, Rachel. So where would someone like Rachel, an entrepreneurial and intrepid geologist, go to? So what she might do is she might just go to USGS and oh boy, let's latest earthquakes. And so here's earthquakes from today, the last day. Let's broaden the scope a little bit. So let's find an earthquake for Rachel, shall we? Let's do 7 days. Okay, so Rachel, let's say you are super interested in this earthquake off the coast of Mexico, right? For whatever reason. So you can click on the dot, then click on the blue down here, which gives you the magnitude and some information. And it doesn't show up here, but usually if you go over to technical, oh, they don't have one for this one. Okay, that made me a big liar. All right, Rachel, let's find you a different earthquake. Usually they're on there. I think sometimes it depends on, because I don't go hunting for every single quake. Definitely if it's a bigger quake, it's going to be there. So let's broaden the net a little bit bigger, Rachel, shall we? And others that might be interested. Okay, so now we've just changed it to significant earthquakes over the past month. So let's pick this one in Mexico, 6.0. Hopefully, hey, there it is. So it should show up as you just click on the earthquake down there, or you can click on technical and go to moment tensor. So it looks like this was a reverse fault or subduction zone type earthquake, compression. And if we just go back to the map, well, that makes sense because that's a subduction zone right there along the coast of central Mexico. So hopefully that was helpful. Back to the chat, scrolling through. See the quake. Oh, that's David. Quakes near Texas. Let's see anything else. Don't the S waves secondary also give us a lot of data on these quakes? Yeah, Dan, good question. Again, I'm not a seismologist, so don't know. But the P and S waves together will give us information about how far the earthquake is from a given location from the seismometer. I'm sure they provide other information because it's a different type of wave form. And so to a seismologist, I'm sure the secondary waves tell them more about the earthquake. I don't know what that is specifically off the top of my head because of, it's instead of a push-pull wave like the P wave is, it's moving up and down more. And maybe David answered this one. Yeah. Oh, yeah, S waves don't move through liquids. That's true. So let's see, duck and cover. Yeah, so this must be the part of the live stream where we talked about the shake alert. David, you're awesome. David, we should just vote David in as captain of the team, I suppose. I appreciate that. Yeah, and then I went off on my tangent, clickbait, scaremongering. How often does a bigger earthquake happen? Robert Tolman. Not sure what you mean by bigger earthquake. On average, we get a magnitude 8, which is huge, right? A magnitude 8 would be, we get one of those per year on average. So some years we don't get one, some years we do. If we kind of zoom out here a little bit, over the last month, looks like there was a 7.0 down here, Solomon Islands, 6.3, 6.1, Turkey. That was probably bad. Yeah, that was bad. Turkey has shallow earthquakes, lots of people, old buildings. And so even though that one was a small earthquake, that caused a lot of damage. You could probably look up, that was in November. You could probably look up more about casualties and stuff with that earthquake. Yeah, so hopefully that answered your question, Robert. Magnitude 7s around the planet, maybe a dozen or so per year. So obviously, as you go down in magnitude, it's increasing the frequency, how often we get those earthquakes occurring. And I probably have a graphic somewhere that shows that, but I won't take time to look up that right now. Yeah. Let's see, videos, swimming pools, seiches, yeah. Radians, yeah, David explaining radians. Sorry, that's just it's a very precise unit. I think, shoot, I'll mess it up, but basically a microradian is a tiny percentage of a degree or an angle, right? So you could look it up and figure that out probably. Seismic activity went along with the eruption. I think we kind of covered that a little bit. What was the nature of this earthquake with its location over the Gorda Trench? Was 17 kilometers below the accretion. Oh, okay, I see what you're saying. Good question. I don't have a good answer off the top of my head. 17 kilometers. It's pretty shallow still. You're still within the north. Well, was it on the Gorda plate? Now I need to look back at my own stuff. Yeah, I think it's still within the crust there. Yeah, it's in there. Yeah, so it's on the it's North American plate, isn't it? Yeah, so it's on North American plate. So it's probably a case of the Gorda plate shoving. I don't think you're down. So you're definitely not down deep enough, I don't think, although we could play a trigonometry game to figure it out. That we're down deep enough that the Gorda plate sliding under North America at that depth. I'd have to figure that out. It's a really good question because what we want to do is measure the distance from the plate boundary over to the earthquake, then make a triangle, a right triangle, go down 17 kilometers and see what that angle looks like and see if that's reasonable or not. So really good question, John Nash. Wish I had all the good answers for you, but I tried. Lots of well wishes. Happy holidays. Was this earthquake indeed? Oh, David asking me a question. Wow. A very shallow version of the Nisqually. I don't think so, David. I'd have to look back at the Nisqually quake, which was 2001 or 2. That was more of I mean, it's ultimately caused by the subduction zone, but it was on a different fault system too. It wasn't as close to the plate boundary. Yeah, so I don't think we need to worry about, this quake triggering some big cascading event. You just saw with that fun Christmas light animation how many quakes have happened, much bigger sometimes, in the Mendocino Triple Junction area, none of which appeared to have triggered any bigger quake in the region on the Cascadia subduction zone or any other place. Robert wants to know about my thoughts on Baja, BC. I don't know enough to have where am I at on the 1 to 10 NICS spectrum? I don't know. Paul Umhofer was my advisor at NAU, but I did a master's project down in Baja California in much younger rocks, unrelated to the whole Baja, BC issue. And so I know a little bit about it, but I need to probably catch up on all the live streams and everything Nick's done and some of the literature to really make any sort of educated opinion. So I'll just say I'm too ignorant to have much of an opinion, I suppose. Let's see, Green Beach on the main island. Oh yeah, I've been there. That's a good question. I'll go with Chris's question for now. He asked about, can you elaborate on Green Beach on the main island? So down here at the south end of the big island of Hawaii oh boy, now I got to find it. Just follow all the Jeep trails. They'll take you there. Oh my gosh, what a nightmare. Here it is. This little area here. Oh, I guess I can't zoom in any further on USGS site, but this is the green sand beach. This is all olivine sand. I guess I didn't even get to your question, Chris. I got excited. How does all olivine sand end up in the ash that cause this beach to be green? What are why are there small pieces and not large chunks of the olivine crystals? Great question. So shoot, what should I do here? Maybe switch to Google Earth. So if we get in close, if we can get a nice image close of the green sand beach. So let me take you back over there. What we'll see is that the green sand beach area has an anomalously large amount of olivine there that has weathered out of the rocks because it's not just basaltic lava flows that are there, but there actually is a cone, what we call a littoral cone, like a rootless cone. So basically, the water and the lava were interacting. I don't know why my computer's being so slow. And fragmenting and breaking up. So let me back up. When that eruption occurred, a lot of that olivine had already crystallized. So the lava coming up already had significant, meaning, maybe a centimeter or so across olivine crystals within it. So that was carried by the lava upwards. Had it just formed a lava flow, you'd have all those olivine crystals embedded in the lava flows. But as it happened, the lava flow entered the ocean and became explosive. And so it's fragmenting the lava into smaller and smaller pieces. And those pieces have big chunks of olivine in it. Sorry, my computer's being so slow, folks. And so here we go. Let's see if you can even tell. I've never tried this. You can see the green. Yeah, so this is the green sand beach, Manaha Bay. Yeah, this is a great place. So, and anyway, so what you can see here in these bluffs, well, hopefully, and I apologize, this isn't the best view, but it's bedded ash, right? So this is pyroclastic ash and particles of lava that got thrown out because it was interacting with the seawater, became explosive. And so the material that coalesced there was ash, or what we'd call tuff, I suppose. And so it's very soft and friable, easily eroded, and then it can concentrate those olivine crystals on that beach. So it's a consequence of the eruption becoming explosive because of the interaction with the water that allowed so many olivine crystals to be concentrated on the beach. Hopefully that works, Chris. Good question. Let's see. Anything else I missed? Is yesterday's likely to affect Cascadia? No, I don't think so, Anne. Like, sleep well. Yeah, I mean, and hopefully, if nothing else, I think the most dramatic thing I showed you was the the Christmas light 40 years. So this Mendocino triple junction has been having magnitudes 3, 4, 5, 6s, and even 7s for 40 years, and even way before that, none of which has triggered any bigger event on the Cascadia subduction zone. So I wouldn't worry about it. Yeah, David corrected me there, unless, yeah, 8.0 per year, not in the US. Per your last Yellowstone video, why wasn't the baked sandstone you pointed out not covered by the 30 or so older eruptions? I think you're referring to the one I did the big hike up by Mammoth, where I had the Huckleberry Ridge tuff. And I guess so it wasn't exposed, right? So that sandstone was probably underneath younger rocks during those older Yellowstone eruptions. And then it gets eroded down. The Yellowstone landscape has been incredibly dynamic in terms of how much uplift erosion has occurred. Then you have that Huckleberry Ridge eruption 2.1 million years ago, and then you get that ash put right across the top of that sandstone on that specific day. But if you erupt that ash, a couple thousand years earlier, then there's a different topographic surface, a different landscape for those to be deposited on. So hopefully that helps, John, but happy to follow up with that if you need to. Okay, I got to the end of, yeah, Rachel, you should go to that beach. It is hard to get to, but you can actually take, if mobility is an issue and a 3-mile hike slog, it's always hot and windy down there. If you either have a rental Jeep, or sometimes there's locals hanging out at South Point, usually not super shady, but they'll usually if you can pay them, they'll take you out there in a Jeep. You can drive the roads and go right out to the green sand beach. Supposedly only one of two in the world. The other one I think is in Guam. So awesome. That's it for me, team. I'm glad the coughing wasn't too bad. Hopefully it wasn't too distracting. Hopefully that was helpful. We covered a lot there. Sorry about the tangent. Hopefully it didn't feel too aggressive, but mainly just wanting people to get good information. I don't care what people do with their YouTube channels, but I have to admit it's a little, it hurts me in my heart, my scientist heart a little bit when I see, me and Nick with our couple thousand, well, Nick's got like 50,000 subscribers, which is great. I mean, and I've got 11,000, whatever. That's great. But then you see some of these fringe earthquake conspiracy people with, 500,000. It's like, oh my gosh, what's going on in the world? So sorry if that was a bit of a tangent. Don't know when I'll do another one, but if there's another big event that happens, or you have a specific topic, a piece of content you think might lend itself well to doing more of these live streams, I'd be happy to do something and put it together. This one was thrown together, excuse me, somewhat quickly by a viewer that had asked me some questions about, I think it was Tony, thank you, Tony, in California, about this earthquake. And I'm like, well, maybe I could do a live stream about it. I've got a little bit of time. So apologize with some of the graphics and stuff that weren't super slick and produced, but you get what you pay for around here. So everyone have a great Christmas holiday. Stay safe, stay well, enjoy your time with family and friends. I'll be here on the flip side. Look for more rock identification videos. Do all the like, subscribe, share things that help the video get to more folks. That's always helpful. And yeah, I'll see you guys at another time. And great. Enjoy. Appreciate spending time with me this evening, or whatever time it is where you are. And that's all. Thank you. Goodbye.